The Indian Association of Structural Engineers, also known as IS-Struct-E, was conceptualized and constituted in the year 2002 by a group of senior professional structural engineers from all over the country. IS-Struct-E is registered under the Societies Registration Act 21 of 1860. IS-Struct-E is a national apex body of structural engineers in India with a mission to promote structural engineering profession and cater to the professional needs of the structural engineering fraternity. In the short span of 2 decades, association has attained an eminent position in the professional field. Its membership is valued very highly in the profession. Since inception, IS-Struct-E has been led by eminent structural engineers like late Shri Mahendra Raj, late Shri Shri Kumar Ghosh, late Shri Subhash Chand Mehrotra, Professor Mahesh Tandon, Shri Manoj Mittal, Professor R. Pradeep Kumar, and Shri Alok Bhaumik as its president. IS-Struct-E is a permanent member of Engineering Council of India and interacts with the government on professional and policy matters related to civil and structural engineers. To expand its reach, IS-Struct-E has collaboration with various international professional like-minded associations and institutions like IS-Struct-E, UK and FIB for strengthening global connections and professional exchange. IS-Struct-E's prime objective is supporting and protecting the profession of structural engineering by upholding professional standards and acting as a mouthpiece for structural engineers in India. IS-Struct-E endeavor to ensure that its members develop the necessary skill in structural engineering and work to the highest standards by maintaining a commitment to professional ethics and standards. IS-Struct-E is actively engaged in organizing several continuing professional development (CPD) courses for structural engineers to help them update their knowledge and advance their career paths. It also conducts refresher courses for young and practicing engineers and student-oriented programs. Seminars, workshops, conferences, technical lectures and discussions related to the latest technological advancements and case studies are also organized regularly for members to enable them to continuously update their knowledge and skill set by interacting with the best minds from the industry. IS-Struct-E's activities are widely appreciated and known for quality technical contents. IS-Struct-E is also actively engaged in publishing its quarterly journal Structural Engineering Digest (SED), code commentaries, professional guidelines, monthly newsletter, and Crossfall, a unique quarterly newsletter that confidentially reports structural failures and the lessons learned from them. IS-Struct-E's publications are becoming popular with time. IS-Struct-E has representation in various technical committees of BIS and IRC as well. Its members are actively contributing to National Code of Formulations. In the year 2020, IS-Struct-E started National Awards competition to stimulate interest in the structural engineering field and to promote innovative thinking and creativity. The awards are presented to the winners in recognition of their outstanding contribution to structural engineering in the categories which include Outstanding Structure, Outstanding Structural Engineer, Outstanding Woman Structural Engineer, Promising Young Structural Engineer, and Best Master's Thesis in Structural Engineering. Reaffirming its commitment to professional excellence, IS-Struct-E launched the accreditation program in 2023. This flagship initiative empowers practicing engineers to evaluate their competencies, identify growth opportunities, and strengthen the foundation for sustained professional success. IS-Struct-E is currently operating from 4 regional centers, namely Eastern, Western, Northern, and Southern, having its headquarters in Delhi, to inculcate the professional culture and provide handholding to the budding engineers. Joining IS-Struct-E offers exclusive resources, mentorship, and networking with industry leaders. Members enjoy discounted registration for workshops, seminars, and events, along with discounted membership of FIB, opportunities for certification, career guidance, leadership roles, and enhanced professional recognition. IE Struct E has its student chapters in several leading engineering institutions as well. Membership of IE Struct E is open to all civil and structural engineers engaged in structural engineering profession. Members are elected based on their qualifications and experience in different grades as per eligibility requirements prescribed in the bylaws. Each application is carefully scrutinized before electing the members. More information about IA Struct E is available on its website www.iastruct.co.in.
Yeah, good afternoon, everyone. ISTECT is hunger for the knowledge and continuing in a keeping another session, a beautiful session of UHPC from philosophy to engineering. We are very lucky and fortunate that Dr. Bijily uh, is moderator for this program. As the name suggests, this is a philosophy to engineering. I will say that Dr. Satish Jain, who himself is expert in a UHPC, and Dr. Bijily, who is doing lot of R&D on the UHPC, and that's very soon will be the norms in India for the very future. And uh, I will hand over to Dr. Bijli. But before that, we are fortunate that Mr. Alok is also there. Our president, Mr. Alok, is also here. And I will request him to say some words without before the start of the this web session.
Thank
Mr. Alok.
you, Sandeep. Am I audible?
Yes, you are audible.
Okay, so welcome to the first webinar that we are having in 2026. I wish all the participants a very happy new year, a very happening new year, and I hope that this year we will bring in new technologies, sustainable growth, and whatever we are talking about for the future will all come through in a substantive way in this year. I also welcome our speaker, Professor Bijily, and also Dr. Satish Jain. I know both of them intimately, and they have been doing some pioneering works in the field of ultra high performance fiber reinforced concrete. A lot of research, and also in the helping the IRC for developing a code or a guideline on UHPFRC. So with this, I would not like to spend much time speaking myself. I would rather like to hear the experts, and I would hand over back to Mr. Sandeep to take it forward.
Thank you, sir. Thank you. I think I will also let's start the session, and I will hand over to Dr. Bijli for his moderation of this very important program on the UHPC. Over to you, Dr. Bijli.
Thank you, Mr. Sandeep and Mr. Alok for the wonderful words. Good afternoon, everyone. For a wonderful evening at the early of 2026, we are starting with a very relevant topic. On behalf of organizing committee, I warmly welcome all of you to the technical section, UHPC from philosophy to engineering. Ultra high performance concrete has evolved from a niche material concept into a transformative engineering solution today. It is influencing how we design today, build today, how we strengthen and future-proof infrastructure. Today's section focuses on philosophy behind UHPC and to its engineering realization and the field implementation. Introduction of this speaker is not required for people who knows about UHPC. He is a pioneer in UHPC in India. Dr. Satish Jain holds PhD and MS in structural engineering from Iowa State University, USA, and he is a licensed professional engineer and a structural engineer. He brings almost 24 years of professional experience in structural engineering and construction, with extensive involvement in the process of holding India, especially in the area of UHPC. Dr. Jain is currently the Managing Director of UHPC India Private Limited and is widely recognized as a pioneer in the adoption and application of UHPC in India, both for the new construction and also for the strengthening of existing structure, which is one of the very important aspect of India today. Because being the structure what we built over years, now we have to ensure that we are strengthening them or retrofitting them in the appropriate way. He is credited with establishing India's first commercial indigenous UHPC premix manufacturing unit in India, and I have visited his plant. It's a wonderful place. In addition, Dr. Jain served as a chair for UHPC Technical Committee of Indian Concrete Institute and is a member of IRC subcommittee for 4.5 on UHPC. With his strong academic foundation and deep industry experience and the leadership in the standardization effort, Dr. Jain brings a unique perspective that bridges material philosophy and engineering practice. We are very confident that today's talk will provide a valuable insight into how UHPC transitioned from a conceptual philosophy to a robust, implementable engineering solution. Dr. Jain, we look forward to your presentation. Over to you. Thank you very much for agreeing to deliver this particular presentation.
Thank you so much, Dr. Bijily, for having me over here and for the really kind introduction, towards this talk today. Thank you so much, Mr. Sandeep Patiwar and Mr. Alok for making I succeed, overall, basically. First talk of 2026, and as Dr. Bijily mentioned, it's a very relevant topic today. And I think the topic itself, if it was probably 5-6 years back or 7 years back, probably you had to stop everything from very, very, very basics, or probably most of the people would not have even heard about UHPC at that point in time. But all these years which have passed by, and today at least people are aware. They have heard about UHPC. They know that different kind of work is going on UHPC, and so let's talk about it today. What I'll do is my headphones are giving me a little bit of a problem. I'm going to just take them off and get back to just get back to the regular laptop.
Can you start your presentation so that at least your doctor, your presentation, can you start it?
1 second.
Yeah.
As we start talking about.
Yeah.
Can you hear me?
Yes, we could hear you very well.
Yeah.
Can you hear your screen, sir?
I'm back to normal. My screen, unfortunately, I've been trying to get on the Indian Association of Structural Engineers screen. It's not coming through, but and I'm traveling here. So I'm in the middle of the travel and middle of a meeting, just getting through this.
Yes.
But let me start sharing. And how much time do I have to present over here?
How much time you needed, Dr. Satish?
Okay, all right. So let's put it this way and try to move in the right fashion.
Yeah.
Great. Okay.
We could see your screen. Now we are seeing your email. You could move to the presentation. Yeah.
Yeah. Perfect.
Yes, perfect.
Great. Right. So, as we delve into this new year, and we want to talk about this new, wonder material, so as to speak, which is gaining prominence in the construction industry. Let's put it at the very basics, right? I mean, at the end of it, it's a material, right? It's a material that has some tensile properties, some compressive properties, and due to it, it has some flexural properties and some shear properties. So at the end of the day, if you have a homogeneous material like this, and if you are able to use it to take care of some, structural stresses and strains, then it's a material that you can probably use in, structural engineering. And that's what we are trying to, look at today. Plus, a unique perspective, being this material, it's a very flowable material. I mean, if I show this video and if it's streaming through properly, you can see that this material just flows through like a self-compacting concrete, and it will fill up any shape and size as you want, which is the beauty of this material. But one of the things that you will also be able to see on the screen over here is this material is devoid of any coarse aggregates. So all it has is, really, really fine aggregate. So more than concrete, realistically, it's a, homogeneous composite mortar. That is what it is. And that is what we are using. So, and we'll be talking about the beauty of this mortar. One more thing to realize is this mortar has a lot of steel fibers. We'll talk about the advantage or the need for steel fibers as well. But due to the presence of steel fibers and this being more of a mortar, it is, sometimes more appropriately in Switzerland, it's called as an ultra high performance fiber reinforced composite, more than concrete. And it's aptly called so, right? The beauty being, when we use the word ultra and, not use the word strength going along with it. Typically, we say, we talk about, normal strength concrete, then we go to high strength concrete. Of course, we have high performance concrete. Similarly, over here, we have ultra high performance concrete, right? So we are not really talking about the strength aspect of it. More or less, the strength is given in ultra high performance concrete. But there are certain performance characteristics that are really, really important. We'll just go back to this slide over here, right? And the performance characteristics that we are really talking about, one you're able to see is the flowability of the mix, right? It can take any shape and size. Secondly, what is really, really important to note that ultra means ultra high mechanical properties and ultra high durability properties, and we'll shed some light into it. One more thing, because it's a structural engineering kind of convening gathering today, the beauty is that if you can think about it and if you can design it, you can make it happen. So I'm going to show you a little bit of a crazy looking beam right over here. And this is about a 14-meter beam that is going on a building high-rise multi-story project in Mumbai right now. I'll tell you the need for it and what this particular beam is able to do. But I just wanted to, right at the start, give this particular beam up front to you to kind of get that in the mindset that there is a lot more that can be done with ultra high performance concrete or composite over here than regular or normal concrete. And the beauty is, if you think about it in a very, very simple fashion, just as a material, and you're able to design it, which, by the way, we are all working very hard, everybody is working very hard on putting the code together, then you can come up with anything that you wish to, right? So let's delve into the philosophy a little bit, right? Of course, I have a lot of slides to show on the application side of the thing, but I think it's for those who are still not aware, it's very important to understand the philosophy. We spoke about the fibers, right? Generally 13 fibers, but now a little bit 20 fibers are also being used. So 0.2 extremely fine with a very, very high dosage, typically about 2% of volume of the UHPC. So when we say 2%, it's about 156 kilograms per cubic meter. And when you talk about it, I'll straight away take you to the slide at the top right, or the pic at the top right, which shows, axial stress versus strain curve, and you are simply able to see the difference over there, right? When you have concrete, it can gain some tensile strength, and then you have a brittle failure. Whereas in UHPC, it gains the strength, and then you have a post-peak strain hardening behavior up to some point before you get the strain softening. In effect, you get a almost rectangular, curve in the stress strain behavior. And the beauty is that this means that your flexural toughness or the energy dissipation or the energy absorption characteristics are far, far greater than that of concrete. It also means that, for those of us designers over here, they will be able to appreciate the fact that when you take a cross section and if you have a neutral axis, typically below the neutral axis, you're not utilizing the tensile properties of concrete, but in UHPC, you just simply take that tensile stress strain curve and you put it below the neutral axis and you're able to get, the tensile benefit from the UHPC in design. And that is why sometimes, when people say that there's hardly any reinforcing in UHPC or there might be no reinforcing in UHPC, the reason thereby is that you do get, sufficient or, a significant amount of capacity building out of the UHPC intention as well. Of course, at the same point of time, I would say if you have pre-stressing and rebar along with it, you can have any permutation combination that you want to have to get a more efficient design. Strength. Why do you get such a high strength? I've written somewhere in the range of 140 to 220 MPa. I mean, in the latest US code, they have even come down to 120 MPa for that matter. But the reason you get the high strength is, a real tight particle packing of the UHPC. And when I mean particle packing, you're taking the fine aggregates, you're taking all the powdery material that is there in this mix. When I say powdery material, I mean cement, the pozzolans, like silica fume and maybe fly ash, maybe GGBS. And then, of course, any filler that you might have. And of course, the sand post that. When you have all these things together, all you do is a good particle packing so that the voids are lower. And when the voids are lower, you get a significant amount of compressive strength. You will also look at some material characteristics, other material characteristics over here. The elastic modulus typically is in the range of 48 GPa to 50 GPa. There are certain UHPCs though, mind you, there are certain UHPCs that can reach as high as 70 to 80 gigapascals as well. Now, some of those might be used mainly for impact or blast resistance, etc. Typically not used in general construction, but nonetheless, they can be used. They might be just more expensive. Similarly, in terms of mechanical properties, the creep is quite low. If you just do a normal curing like concrete, your creep coefficient is just about a unit, right? As against concrete, which is about 2.0, maybe 2.2, maybe 2.5, depending upon the grade of concrete. So the creep is low. Now, if you steam cure the UHPC, the creep might also go down as low, depending upon the mix. It can go as low as 0.2, right? You're getting closer and closer to structural steel out there. But the biggest beauty of all, why I believe UHPC is being used, is the design shear strength. The design shear strength is very high. It's imagine, not having any rebar and having just the fibrous UHPC, you may be able to reach about 10 MPa or even 11 MPa in your design shear strength. Plus, then you add rebar. Now compare it with concrete if you want to. Typically, if you pick up the IS 456, you will see in general concrete plus rebar or stirrups, you're allowed a max of about 4 MPa. So 4 MPa to 10 MPa, that's a huge jump. And there is an advantage to this jump. And I'll show you that. And I'll show you that in this picture, right? Imagine having a rectangular beam. And because the beam is rectangle and concrete, let's say concrete as a material, you're going to utilize the concrete shear strength. You're going to utilize the stirrups contribution, right? But as I mentioned in UHPC, you have a very, very high shear strength of the fibrous matrix itself, that you are able to carve out the sides. You're able to carve out the sides. Look at the leftmost picture, right? You're able to carve out the sides of this particular beam because you no longer need that kind of a web dimension, right? Or the web width. So once you are able to take out that web width and take out and carve out the material out of the UHPC, you're left out with a much lighter beam. And that is why I just mentioned a couple of minutes back that the shear capacities in UHPC are a major contribution as to why actually UHPC is being utilized today, is because you can lower the weight of your UHPC beam to as low as just about 40% of a pre-stressed or a post-tensioned concrete girder, right? Even more for a, as compared to a reinforced concrete beam. And just look at the next, I mean, this is a very common slide. This is available on the internet, but look at it. We are now started comparing it to the size of structural steel, right? Even the depth. So the depth in general will reduce by about 30 to 35%, 36%, but your weight goes down as much as 60%, 62%. It's a very important consideration of UHPC. Another thing to also remember is a question that always gets asked, because sometimes this question will come in, so I'll probably answer it first, as to if I'm just designing a beam, why do I need a strength of 150, 160 MPa? Am I going to be utilizing that kind of a compressive strength? So here's the answer to that question. Again, I'm going to go back to this particular, stress curve over here, or the section. And if you look over here, and you're going to design a UHPC beam, you're never going to come closer to the 150. Never, ever you're going to come closer to that. But the compressive strength is important only from one point of view. You can put more and more pre-stressing, force into the beam or into the girder, right? And when you do that, you're able to go longer spans, much more longer spans. And that is why, the compressive strength is important when it comes to the design of UHPC beams or flexural members as such, right? So that's an important thing to remember. Now, if this was just a column, you would be just looking at, the size in general. It's a pure compression, right? Almost a pure compression, a gravity column. And you can, if you're designing a M50 grade concrete column versus a UHPC column, you can take out your ratios and come out with a much smaller size column, and we'll show you that in a little bit. But as far as the flexural member is concerned, the post tensioning plays a major part in getting into those longer spans with respect to the compressive strength. And so the compressive strength itself is quite important. So, I mean, I've already given this comparison. Let me move a little bit forward, and some mechanical properties that we have not spoken about before I move to durability. I also need to say that UHPC has excellent abrasion resistance, right? One of the things that UHPC is hardly used for in our industry right now is the abrasion resistance of floors. I mean, it should be used. There are so many industrial slabs where they have forklifts moving inside. They have heavy duty machinery, operating, and bobbins falling down on the industrial floor. And the industry, these kind of industries, right, the bigger industries, they are in need of highly abrasion resistant floors. And UHPC is one of those things that can actually come to the rescue of these concrete floors. So even a small topping, right? You don't need the entire floor thickness out of UHPC. Even a small topping is going to help it. Similarly, UHPC goes in huge, usage when it comes to, let's talk about impact resistance or blast resistance. These are the kind of, mechanical properties that UHPC possesses, right? And there's so much to gain from it. Now, coming to durability, you can imagine India being such a huge country putting in tremendous amount of money into infrastructure. What will happen if you in a few years down the line, if you want to start maintaining all that infrastructure, right? Maintenance is important, strengthening is important over the lifetime, right? And you're going to just infuse money again and again. That is where this left side picture shows, in the orange curve over here, you see that you design for something, it deteriorates over time, then you're going to strengthen it to the most current code or the most current requirement. Again, it deteriorates. Again, you're going to strengthen it. So at least there are going to be these, 2, 3, 4 occasions in 100-year lifespan of probably a bridge where you're going to be putting money into the bridge. Not only money into the bridge closes cost money in terms of time, the traffic that comes with it. But have a look at the black curve over that. So if you're just going to repair it with UHPC, just a small layer of UHPC on top of your decks, or if you're going to build a new structure with UHPC, right? It's just a one-time solution. You will never have to touch it against as far as maintenance is concerned. Therefore, this material is also called a material that gives you about 100-year maintenance-free life cycle, not just a 100-year life cycle. We're talking about a 100-year maintenance-free life cycle. And that is why this material today is quite important and very important to the infrastructure in India, because it can save so much in the long term for the country. Yes, maybe the initial costing here or there might be a little bit higher, but in the long term, believe me, the country is going to save immensely, and that money can go into various other things, in fact. So the right side just shows, a unit comparison between concrete, high performance concrete, and in blue, if you can watch, if you can even see in your screen, that's UHPC. So this is with regards to permeability, chloride ion penetration, and corrosion rates and carbonation rates. You can see that UHPC is, way, 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 way lower than concrete. And that is again the reason that you get that 100-year maintenance-free life cycle. So that's the beauty of UHPC. It brings the best of the mechanical properties and the durability properties together, and it is giving us something very unique today, which probably 30 years back, at least in India, we were not able to recognize that. But today the recognition for the material is there. It is definitely there, and it is gaining prominence. It is gaining such prominence that all major, whether you call it government institutions or educational institutions, they are all looking at it very closely. And the private sector, the construction companies, the consultants, the design engineers, they are all following this extremely closely to see how they can fit this material to give some kind of a value proposition in the project, or do some problem solving in the project for the long term. So that takes us a little bit further into it. We till now I've just a little bit talked about flexural members, touched a little bit on compression members, but UHPC as a material also has excellent bond properties with reinforcing steel, and that is not to be neglected. Believe it or not, if when it comes to European countries and the Americas, they are in fact using a lot of UHPC for joining or stitching of precast concrete members. And the left side, you can see that comparison so well. This is a bridge deck. The left side is a conventional concrete stitch versus, the second from left picture just shows a UHPC detail. Now, to tell you very simply, if you look at the rebar development length in concrete, we are typically talking in the range of 35 times diameter to about 50 times the diameter, right? But when you look at UHPC, the rebar development lengths are just about 15 times the diameter. In fact, it is the Swiss code that says about 15 times the diameter. If you look at the latest AASHTO recommendations, right, they pretty much say 10 times the diameter. But, you can imagine that the stitches and the joints get very, very thin, and they are quite robust. In general, when we say joints, we say they are the weakest links in any kind of connections, or any connections are the weakest links. But here, the UHPC connection or the UHPC joint is quite robust in itself. So you can see this pics on the right side. That's right top is bridge deck, and you have some longitudinal steel girders, in fact, on that particular project. So the longitudinal steel girders are there, then you have the precast deck on top of it, and all the pocket connections that you see are all UHPC pocket connections, and in the transverse direction, you have a full stitch between the deck panel to deck panel. Similarly, there's been work that has been done in New York several years back now, over a decade back probably, wherein the precast pier cap is being connected to the pier using UHPC. So imagine now there are no couplers over here, no real couplers, no grouted couplers, and the entire joint is not filled with UHPC. If you closely look at the inset picture, if you are able to see that it is only the periphery that is left out. Okay, the center core is still the concrete from the pier. So it is just the periphery where the rebars, are matching, right, or are lapping around each other, and you're filling that up with UHPC, and you're developing the, complete tension in those rebars in that kind of a short joint. So that's a major use of UHPC which is going on around the world. So, talking about that stitch, this is a recent project, that we completed. This is in Nasik, wherein a long flyover was already there. It was a segmental, bridge construction, and the segments were slightly opening up, right? So L&T approached us on that one and said that they have decided to actually open up those joints and fill in that with UHPC. I think IIT Bombay looked at L&T's design, and they, ratified it, and we supplied the material to L&T on it, and you can see that they did hydro demolition right at the top, opened up the joints, and the picture, the third from the right, is taken from the bottom, where you can actually see the UHPC, So there were several of these. There were about 4,000 joints that were actually filled up. It was a very, very long bridge. And I'll tell you that this is the UHPC coming out of the transit mixer. So you can see that UHPC directly actually going into the joint over there. So this is real time, thing, that how, cast in place UHPC is actually working in repair and rehabilitation. And you can, just use a simple TM to actually mix and provide. This is also a project for Tata Projects, wherein the area below the bearing, this is above the metro rail, and this was actually filled up with UHPC rather than any normal grout. So UHPC is finding its way in all kind of connections, and I say it's a great use of UHPC in projects. So coming to it, as we are moving from the philosophical to the actual projects, I do want to show this project. This was the first project in the country, actually, completed in February of 2021. Started somewhere around December 2020. Right when the COVID was going on, and the need was pretty simple. Of course, the floor plate was much bigger than this, but this was a small portion in green where they did not want internal columns. The building was already up, right? So at the topmost floor, they wanted to take out these internal columns, and they wanted to have a solution where we were able to actually create an open hall, so as to speak, wherein the spans would increase from 7 meters to 14 meters. And the point was that the loads on the external columns should not increase. And that is where we first thought, oh, this is a great application for UHPC, and we pursued it. Of course, they wanted the entire terrace to be in concrete, therefore this was not done as a metal deck, steel per se. They didn't want steel in there. But you see the thin UHPC girder in olive green over here that was done. These were 14 meters long. And in fact, compared to the original design, the load on the columns reduced by about 30% overall, because the deck slab was still concrete slab. So the overall load did go down by 30% on this. You can see these girders, unbonded, just 3 unbonded tendons were used, and there were additional rebar that was put in the bottom flange, thin bottom flange, in this particular project, and that was made to work, right? Now, curing of UHPC, there are various formats, coming back to philosophy, various formats. Some people are preferring it with steam curing, but at the same point of time, I would like to say normal curing is just fine with UHPC. Also, when surfaces are quite wide, etc., you could go ahead and use curing compounds and curing agents. When you spray them, cover them over, you might have to put more than a single layer, probably 2 to 3 layers of the curing compound to make it work for you. But you can get those done with just normal curing as well. So steam curing as per is not neither mandatory nor it is something that is required. It's a choice. It's a matter of choice and on the application, whether you're going with steam curing or whether you're going with water curing or whether you're going with a curing compound. And you can see there were several girders made over a period of 28 days on this left side beam, and the average strength achieved on site, right, was about 186 MPa on this particular project. So this was this project. The girders were all casted in November, December 2021. So it's already been, 4 years plus now. Now, I do want to show this video because this is from that first project. And this is the very first beam in the country, that has been made out of UHPC for, practical or industrial or basically application, commercial application purposes. And you can see the UHPC just pour into the thin web and just move inside pretty easily. So when you look at this video and you wonder, whether there's vibration required or not, the important point is vibration is not really required. And one shouldn't also think so much about vibration, because a dedicated vibration of the UHPC can, in fact, what it can do is it can align the fibers, in one particular direction. And you don't want that. you want an unbiased random distribution of the fibers. There are, partial safety factors for fiber distribution which are already there in the codes for design purposes, right? So you don't have to worry about that, but that random distribution is very important because it's not just the flexure. You got to worry about the shear as well. So you need to have contribution of the fibers in all directions as such. And I'm just going to show you now. This is going to be the tallest UHPC project in the world as of now, unless somebody builds even a taller one. Not that everything is built out of UHPC. Let us put one thing into perspective over here. UHPC as a material probably is not here to just replace concrete or structural steel. It can never do that, right? Concrete has its own place, structural steel has its own place. UHPC has to find its own place in terms of how much value it can generate for the project, what it can do for the project, what it can solve for the project. So let me explain the floor plate over here a little bit. If you look at the floor plate closely, one of the things that you will observe is that the columns on the top side are quite small. They are in UHPC, but they are smaller than any concrete column that could have been for this particular project. So that's an advantage that you get. The second thing, if you look at the entire gray area over here, this is office areas here. 5 offices at the top, 3 offices at the bottom. And just at that intersection of the 5 offices and the 3 offices, you have a corridor in there. This entire area is totally columnless, kind of in the middle, totally columnless. So you get an open area, open efficiency that is quite important in cities like Mumbai, wherein you're looking for every square foot of carpet area costs tremendous and is appreciated by the clients, by the customers, etc. So that is one huge advantage that we got out of it. Now this has been conceived as a hybrid construction methodology, wherein all the verticals are cast in place, right? And all the horizontals that you see are precast. And you have 10-meter precast UHPC beams, you have 14-meter precast UHPC beams, and then you have some 19-meter beams that actually serves some more purposes. And so we have actually pieces of concrete precast beams that are stitched together with UHPC. Okay, so plus you see these slabs in there. The slabs are actually pre-tensioned concrete slabs that are also stitched together with UHPC. Now what advantage does that bring? See, when you're stitching the slabs together, right, it forms a diaphragm in itself as compared to a hollow core concrete slab which you're butting against each other, and therefore you have to put a 3-inch 2 to 3-inch diaphragm over it, or a screed over it, to create the diaphragm. In this case, which we did over here, you do not need that additional 2 to 3 inches of concrete over the floor slab, right? So you have a continuous diaphragm in nature just because of the nature of the stitch, UHPC stitch that we have provided. One more thing of interest that you will see, and I showed that beam up front when I started this presentation, which was a very funny looking beam, but I'll tell you the reason for that. Where my arrow is, if you can see my arrow, that area is the corridor. In the corridor there are several plumbing lines, electrical lines, etc., MEP lines, basically HVACs and all of it. They're all running through that place. So we were allowed from the top of the slab to the bottom of the beam, just in that corridor area, right? Just in that corridor area, we were just allowed 300 mm structurally. Now, we cannot have a 200 mm concrete slab and a 100 mm beam below it. That's just not possible, right? So we had to think of something unique. Secondly, all the precast slabs, at least in the bottom areas and then the top 5 offices and the bottom areas of these 3 offices over here, they all sit on top of the girder so that they are compositely connected to the beam, right? But where I have these red circles, there was this difficulty because of the MEP. And I, really did not want that these floor slabs had to be shored or temporarily supported during the construction time. It defeats the purpose. So here is what we did. I'm showing that beam again, and I'm going to show you some details. You see, this is on the back side is the majority of the area where the slab is going to come and sit on top of the beam and is going to be compositely connected to the beam. Then you look to the far right, and we have created some wings, okay, to the left and the right. And the UHPC actually goes to the top of the slab. That means the slab is not extending all the way over the beam, but is going to be connected on the side of the beam. So there, the slab sits on these wings on either side of the beam, and we have created a connection, and in between we have the transition zone. Let me show you some detail of that, PT details. Right at the top, you see the plan view, and so you are able to see the wings on the right hand side, correct? In the middle, you actually have the girder, which is shown. On the left side, we have made a pinned connection to the cross girder, which is there. And on the right side, it bears on a ledge on the beam. If you can see that ledge, it's barely visible. And at the bottom, you're able to see the post-tensioning profile, the transition zone, and how that has been, additively reinforced with stirrups. While the rest of the beam doesn't have stirrups in it, but that transition zone and the 300 zone has stirrups in it. And I'm going to show you the connections. The left side is the transition zone, and you can see that over the wings, you can see the slabs which bear on top of the wings, and then you have the stitch connection that happens to the girder. And on the right hand side, you can see the 300 portion of the UHPC beam along with the wings, over which again the slab bears, and then you have a stitch connection to the overall system, right? So had to look at it quite critically during the in the design and the analyses and the deflections and the localized stresses and those kind of things. But what I want to emphasize over here, that you can do these kind of things with UHPC. It's not impossible. If you can imagine it, you can, if you can design it, and analyze it appropriately, the solution can come together. And that is why, you don't have any intermediate columns, those there, and we have those 14-meter beams. I want to talk a little bit more about this project, but, for those who are wondering, how does this material look on the side as such? Also, here is a scene from the mixer. Here's a video from the mixer where you are able to appreciate the flowability of the mix, right? It's a 3 cubic meter mixer in which UHPC is getting mixed. And I'll just, show it again in a different video. This is sideways. And this is not the same 14-meter beams, but this is a 14-meter rectangular beam at the podium levels below. That beam that I just showed and talked about in detail is the one at the office level. But here is a rectangular girder that, of course, is going to be compositely connected to the slab. And you can see the UHPC flow, right? It's just flowing like water and, going into the girder over here, post-tensioned. and fills up the entire mechanism or the entire mold over here pretty easily. I want to show you some beams. This is that rectangular 14-meter beam all the way through. I spoke a bit about the 19-meter concrete girders. So top right, you can see that those are the precast 19-meter girders, which are, stitched, connected to the shear wall systems. You can see the slab being lifted up, the pretension slab. You can see a bunch of UHPC beams down below and so on. Also, you can see some stitch casting happening on the left side in the video. So just, wanted to showcase some of the things happening on the project. There's a formwork going up, has got nothing to do with UHPC. It's a video of that. But, coming to columns, and I spoke about it for half a minute earlier, it's important to recognize again that with UHPC, you can come up and have smaller columns. And I also mentioned, right, we're not here to, as a material, UHPC is not here to just replace every bit of concrete. This particular project just uses UHPC in this red marked zone, okay, in this particular commercial building, wherein the columns were coming out, in M80 grade, they were coming out to be 1600 by 800, extremely heavily loaded. But with UHPC, we could get them down to 750 by 750. And that's where in a departmental store, there's generation of value for the client out there. And you can actually see those columns after the entire thing was done. In fact, just wanted to show that some of the UHPC which was poured in the joints, and that was just poured through a bucket in a beam column joint or the beam slab joint. Yes, there was a beam column and slab. All three were there. This is just going into the joint over there, and of course it's going to be poured a little bit outside as well. Now, these were the beams, Professor Bijily, when you came in, these were the ones that you actually saw, early on. And the reason I wanted to speak about this for a minute was, again, this is from a design perspective, that when the architect client and we were sitting together, we were, of course, pressing on the thing that we could, shallow up the beams quite further. But then the architect here had an idea. He said, anyways, my, HVAC lines are, moving. The heating and ventilation, air conditioning lines are moving below the beams, right? Can we not just deepen up the beams a little bit and have that HVAC duct go through the center so that we don't have to put anything below. It's just the ceiling that will come down below the beam. So we had to go again, because this was a zero shear region, but still the opening was wider. So we did a little nonlinear analysis on this particular beam, an abacus modeling, just to check out the behavior and the failure mode. And we were able to, come up with these short beams, 8.5 meter beams. Literally speaking, there is no post tensioning in it, and there are only 3 number or 12 dia rebar in the bottom flange in this particular beam. There's nothing much there, just 2 metric tons in weight. That's the beauty of it. Also, this particular project close by, it's a 16 meter. We also did a 19 meter with the same formwork. The client wanted to save on the formwork costs. I don't know if he saved on the cost of UHPC over there, but we did 16 meters. But here is an example. I'm giving these examples, just citing these so that these thought processes, could come handy for any structural engineering design. Now, this was a banquet hall which was 10 meters high with 10-meter high ceilings, and the owner, the typical construction process would have been, to build up all the staging, and then do the concrete beam and the concrete slab all post tension, and then wait out for 7 days before actually stressing them, and then releasing all the staging and all of it, which was time consuming for the owner. So the owner asked us for an alternative solution, and we said, at least for this bottom story, what you can do is you can precast the slabs in concrete. These are 4 meter by 5 meter panels, and they were done on the site. And I said, we make the beams out of UHPC. We're going to put the beams, on top of the columns, and then we're just going to put the slabs in place and then stitch everything together so they are all acting monolithic in nature. At the end of the day, we were able to save a month and a half in construction of the banquet hall because of this. So just giving an idea that, sometimes, it's more than that. For those who are working, wondering whether this material can only be precast, I've shown some cast in place options, but here I'm also showing another cast in place option, is that you can always design your UHPC so that it is pumpable in nature. Now, this is just a ribbed slab, but you would see that, again, UHPC is being poured into a pump, and then through the pump, this material, of course, is going up. This was about 60 meters high, and you will just see the UHPC coming out, and you can see the UHPC coming out, right? You don't see any segregation, etc., which just wanted to point out that yes, it is possible for UHPC to be pumped. You can accordingly, design your UHPC, or you can actually have the material pumped. That's one more way of doing the construction. Although there's a lot of things that could be done in repair and rehabilitation, but I just wanted to show this. This is a segmental bridge girder at the coastal road in Mumbai that L&T was doing, and we received a call actually, and said that they had a burst out at the anchorage zone at the stressing area, right? And you can see there's too much rebar in that zone over here. Very difficult to actually push regular concrete in without having any honeycombs, etc. No wonder, there was a bursting in that region. The solution was simple. Everything was just cleaned out. We asked L&T to clean out everything, and then UHPC was poured. So if you look at the center screen over here, UHPC is being poured into the system, and it just went in very nicely through and through. You can see the UHPC actually flowing inside, filling up the entire area. Left side, you can see the hessian cloth is being used for curing that particular anchorage zone that was filled with UHPC. And right side in the picture, you can see the finished product over there, which they are, of course, stressing. You can see the jack there and the strands also. So the stressing was going on. It just happened really nicely. I also want to show you a couple of things. It's very interesting couple of projects that were completed, where we did a swimming pool and a skywalk almost 70 meters high up in the air between two towers. Of course, there were bearings, and we have a sliding system, etc., for so that during earthquake we do not have anything catastrophic happening. But you can see, if you can look at the top left picture, those are UHPC inverted T beams. On the top right picture, you can see some of those beams, right? You can see the beams being placed. And then what we did is we filled these gaps up, right? We filled these gaps up with a very lightweight material like Modi foam in there. And at the top, this was compositely connected with cast in place UHPC. So although you have an inverted T UHPC, right next to each other, but at the top, they are all connected to each other with cast in place UHPC. That's how the swimming pool was put together. And then you also see at the bottom is one of the beams for the skywalk that was put together. So this skywalk also went, bottom right, went all the way. You can see while the slab was being pulled up. Right. So yeah, you can do amazing things with UHPC. If you can closely design it and detail it and analyze it appropriately, material can do wonder things for you. There's another project, just wanted to showcase a couple of things in it. This was a 35-meter girder on a project, there. But you can also see in the bottom right is it's a cast in place, right? This is a cast in, this is not precast. This is a cast in place girder, actually. And it is looking white because all curing compound has been applied to it, right? So there are 3 coats of 90% efficiency acrylic based curing compound which is put on it. The project is still ongoing. There's just 6 girders on it. The last girder is left out at the moment, so which should get completed soon. So other than that, I do want to show 3, 4 interesting things. This is of course not our project. This is in France, southern France, but there's a reason I want to show this project. You can see the girders, and both, if you want to call them piers or columns or sticks, whatever the name, they're so thin. They're all UHPC in this particular bridge, and it's a 73-meter bridge with approximately equidistant 25 meter 25 meter 25 meter, right? So the center span is 25 meter. But if you look at the right side into this section of this particular bridge girder, UHPC girder, you will see something very interesting. And what is interesting is this is not a fully pre-tensioned girder. This is a partially pre-stressed girder. So it's designed as a cracked UHPC girder. You have rebar and you have some amount of pre-stressing in it. Now, I'll tell you, as of today, such a mechanism has not been used, at least in India, but using the fibers in serviceability as well, is an amazing thing. So the whole mechanism of a cracked UHPC girder is important to understand, and this you can actually come up with even more economical sections, so as to speak, possibly, right? You just have to look at the project and project to project case. But I just wanted to showcase that all the dark black spots are rebar, and the white hollow little rounds here are the pre-stressing, pre-tension, basically. This project I keep showing again and again over the years. It's just interesting because it's a pie-shaped girder and everything's UHPC. All you need to do is put a pie against a pie against a pie. That's what they're doing in the top middle photograph, and they're just stitching everything together, right? At the end of the day, you don't need any wearing course, right? So in the US, on this particular bridge, there is no wearing course, and you just have this whole thing. Once it's jointed together, it's ready to serve its purpose. Also like to show this is where UHPC has been used for as a deck member, right? So it's a waffle deck, and This is on a bridge. This bridge has been at least working non-stop for about over 15 years now, 15, 16 years probably. And no maintenance, nothing wrong with it, until now. Everything is going good. You can see the waffles, and you look at the size. The the flange thickness or the deck thickness of the waffle itself is 65 and the ribs are 200 deep, right? It's a very light deck section. Again, these deck sections are stitched to each other as well, and then stitched to the girder as well, right? Plus, let me put this point down. A very important point to note is the only rebar, in this particular deck is 116, okay, one number of 16 diameter rebar in the rib, in each rib. That is all it is. There is no other rebar in it. Which, I mean, you look at a conventional deck, you will find so much rebar going into it, right? But here you will find that you can actually count, on your fingers, the number of rebar that's going in a piece of a deck over here. And rest everything is just UHPC, and the deck weight is just about 35-40% of what a typical concrete deck would be. Sometimes there's always a good question as to, when we are repairing with UHPC, as to how, a low grade concrete or normal concrete, let's put it as normal concrete, how does it work along, or how does it bond along with UHPC? So just wanted to show this. This is on a bridge rehabilitation project that we did for the dedicated freight corridor. And these are core samples. The concrete part is the core samples that were actually taken from the bridge deck, right? Which were roughened, and UHPC was, poured on top of it. Then, of course, after all the strength gain and all, the slant shear test was done. And you can see the failure. The failure is in the concrete. It is not in the bond or the UHPC. So, of course, we replicated the roughening that we did on the deck to the roughening, onto the concrete that was done over here to showcase that, yes, bonding does happen. Really good bonding happens. In fact, as another project for those in Mumbai can, visit there's a flyover at Targar, which is right next to the Navi Mumbai International Airport that has just opened. One of these spans was fully strengthened with UHPC, and there is no wearing course on it. There is absolutely no wearing course on it. It is just UHPC on top. After all the top 40 of UHPC was taken out. Sorry, concrete was taken out. Old concrete was taken out, and then UHPC was put in. You just have that thing going over without any wearing course. Before I finish up, want to show these amazing pictures, right? Again, long cantilevers, etc. That's all UHPC right at the top. This is a railway station in southern France. Wonderful piece of structure. I've been showing these pictures right now, I believe, for the last eight years or so. It still amazes me when I was there and looked at it, that how, successful engineering can be done with a material like this. Same thing for architectural purposes. You can come up really nice things. Now these are aesthetic things, of course structural in nature, but still very aesthetic. So that's where it is. So right here, yeah, I mean, before I close up, just want to say, you add value to your projects. Use UHPC as a value addition to your project, value addition to the client and the customer, right? Solve their problems. You can think of it, not as a full alternative, but yeah, still some alternate to structural steel. But yeah, utilize UHPC for a betterment of the country, for better durability and everything. So thank you very much. Thanks. A little bit. I want to show those pics, but yeah, they're there. Thank you. I just stopped sharing right here.
Thank you once again, Dr. Jain, for sharing your experience and insight on UHPC. I would also thank you all the participants who was patient enough for an hour time. That's really great. So we have a lot of questions in the question answer section and few are coming up in the chat section.
Right.
What has come up till now, I have actually grouped them so that we will have an effective communication.
Okay.
So let's start with the basic question. The first question from a couple of people is actually the composition of the mix.
Correct.
So there are thought process on cement content. What's the grade of the cement to be used? Cement to binder ratio. What's the water content? What's the percentage of fiber? And from moving on to there, if you can explain the mixer detail, what kind of mixer we have to have, and do the labor who is working on this to have us any specialized skill. We can answer all these three together would be great.
Right. So yes, these are all interesting questions. So simple theory, I think we started talking about particle packing, didn't really go into the mix design as such, right, at the start. So yes, number one, without stating all the materials, I can say all the materials, whatever is used, has to be of excellent quality. Now, coming to materials themselves, sand, you need a sand that is clean, right? So devoid of the silt, basically. So you need, of course, as much rounded or as much cubic sand in nature, so that the flowability is there. You need it washed and dried. You do not need moisture content in the sand there. And you want the sand to be as fine as possible. Typically, I think in the code, we are probably going to recommend, anything 2.36 mm and lesser. But some of the material that you saw on the videos over here, they are actually lesser than 1,000 microns. So they're, you would see a lot of them, 600 microns down, 800 microns down in terms of the sand. Also, the sand, you want extremely low absorption on it, extremely low absorption sand, so that the water absorption, water in the UHPC is low, typically about, anywhere in the range of plus minus 0.18, right, of the cementitious, right there. So you want that to be on the really lower side, and you don't want to lose that water, right? So you have to use a low absorption sand. You are going to use some content of silica fume, just because the silica fume are the finest particles in there, and thereby filling in the pores and the voids. They're going to be the most robust form of resistance to anything which is going to deteriorate the material. So it adds to the durability out there. Now, when it comes to cement, right, sand could be about closer to a ton in a cubic meter. Cement could be in the range of anywhere in the range of general, if you're just going to add cement, 700 to 900 or whatever, right? But today I can also tell you that you could devise mixes that can have anywhere even 50% GGBS content on it, 60% GGBS content on it. If you're adding fly ash, you can come up with these binary and ternary mixes actually for UHPC purposes. So from application to application, those can change. Of course, the cement kind that you want to have, what you have to do with your mix is, you don't want very high heat of hydration. So you have to devise it so that you have, longer setting times, low heat of hydrations early on. That's one big point that has to be noted. Now, when it comes to the mixer specifically, the mixers, general mixers, you can use planetary mixers. High energy mixer really helps to mix very nicely and in lesser time. But planetary mixers, twin shaft mixers, they both work really well. But I'll tell you, we have also devised mixers so that they can be mixed in a transit mixer as well. Okay, not that you want to just try it randomly, but you should, if you want to mix it in a transit mixer, then you have to devise a mix accordingly that works appropriately to that. But yeah, you need to have some form of high energy. You cannot just use a very simple drum mixer on a site, the ones that are there about that can mix 300 kgs or 400 kgs, that can do that, typically are present on the site. Please don't use that. Thing again to note is during the mix, use some amount of ice. Okay, if not fully, you can use 100% of ice too, but I would say only when the temperatures are nice and quite low, that you can be devoid of ice. You need to use chilled water though, 4 degrees Celsius and below. But in general, if you use 20%, at least on the lower order, 20% ice and 80% chilled water, and when the temperatures are really high, you can reverse that ratio as well, 80% ice and 20% chilled water. You can gauge it on your site based on the temperatures as to how much the ice to ice to water ratio has to be. So that's about these things. And from a perspective of somebody who's going to be uh, cast or mixing and casting on the site, believe it or not, at least right at the moment, I say that we are not talking about mixing all the raw materials independently on the site. Probably it's going to be a mess out there, but typically either it's going to be some kind of a partial premix or a full premix that you're going to be putting into a system, which is a mixer or a TM, whatever it is. The two things to be very careful about is you're mixing the right quantity of water/ice and right quantity of steel fibers. You're making sure that if it's a transit mixer, then you're giving enough time for the dispersion of the steel fibers as well. But if it's in a mixer, typically it was dispersed off pretty fast and very easily out there. So, I mean, some points that do come into my mind. One thing that I always say is if the temperatures are extremely high, like close to 38, 40 degrees on site or more than that, go ahead and cool off your mixer first. Just put ice into the mixer for 10 minutes, 15 minutes, run the mixer, cool off the drum, and then start your mixing after that. It really helps.
Yeah, thank you. I think you have covered up very well. You have also answered thermal behavior. That was my second question to go. So, thermal behavior of the mixture. There is one more question which is associated with it. Can we use it for massive concreting like dams or no big thicker raft? People have tried it or not. It is connected, so I thought
I mean, can it be put in? Yes. But do you want to use it? Probably not. It's not going to be economical at all if you run the numbers. So technically, yes, but economically, probably not. In fact, I can tell you, one can try out some independent footings if you can create a mold that looks more like a base plate with stiffeners, right, and steel. If you can create a foundation like that, that would be economically.
Slab.
Yeah. It's just a thin slab with stiffeners coming out, made out of UHPC. Even the thin slab is UHPC, and it will act like a footing for you. But I mean, these are far-fetched thoughts. Could always be tested out and used, but that's probably one way to use it in a footing. But
one another question associated there is the availability of silica fume. Do we have any SCM substitutes for it?
So so SCMs, yes, you see, that's a good question. Yes, you can do quite a bit of substitution with your other highly reactive pozzolans, the highly reactive GGBS extra fine or highly reactive fly ashes, but leave a little bit of silica fume for what I mentioned for the durability purpose, right? It still fills up the smaller gaps, right? So you do not need to mix 100% silica fume of what is required, you can do some kind of ratios on there so as to reduce the quantity of silica fume over there.
Yeah. So related to the pumpability of the concrete, did people tried any time UHPC pump it over a higher height and did a casting situ casting?
Yeah, so I think that is one video that I showed wherein we pumped it 60 meters high, and we have done it on a few good projects now where we have pumped UHPC, for ribbed slabs, for girders, etc. Where has been highly successful without any issues. Yeah.
What are the current cost of UHPC in India?
Really varies depending upon, of course, quantities, applicabilities. You can say, in general, if it's mass, you're going to be doing massive amount of UHPC on a projects. Those numbers could come down to 75,000 or something, 80,000 cubic meters or 85,000. But if you want to do smaller projects, 100 cubic meters, 200 cubic meters, probably maybe in the range of 1 lakh cubic meters. If you're doing overlays require the thin overlays. When I say thin overlays, 40 millimeters, 30 millimeters, these overlays require, all right. So these overlays require, uh, about 3% steel fibers out there. So they become even more expensive. You add up another, it may be 1.25 lakhs or something. And then you're talking of UHPCs on some very high impact and extreme cases. Those UHPCs can even go to 2 lakhs or something like that in nature. Yeah.
Can I extend this question further? See, when suppose if you say that the cost of the UHPC concrete is something around in the range of 80,000, depending on the volume and all those things.
Yeah.
What content is the important which is increasing the cost? Can it be the reduce in the future, or what is the require? Why it is? See, when we say the normal concrete is say around 5,000 per cubic meter, and this of course, if you consider the reinforcement, it may come to 10,000 or 12,000 per cubic meter. Why it is, of course, there are advantage. You reduce the quantity, you reduce the volume and all those things. But what is the content? What is the material which increases the cost of the UHPC?
See, there are 2 points. The material itself, yes, the steel fibers themselves are expensive, right? Maybe about anywhere in the range of 100 and 60, 170, 180 rupees a kilogram out there. That is from a material standpoint of view. But again, from a material standpoint of view, what is really important is the quality of the material, and the standard deviation you want to keep very small on the quality of the raw material that is coming in. And so the extensive cost that goes into making sure that these raw materials may not be just available right in your nook and corner, out there. Some of them you have to get it right. You can get it from the country, but you might have to get it, from far-fetched places in the country. And these start adding to the cost in terms of transportation, and of course in terms of quality control, because you got to check, I would say, every batch of raw material has to be quality checked in your laboratory before it is actually going out to the site or any other place. And so there is a human intervention, to that, plus the high cost of R&D that is continuous to the making, from an industry standpoint of view. So it has nothing to do as such with just the raw material itself and what is the cost of raw materials. But at the end of it, you got to make sure that you're not losing a batch on the site. If you lose a batch of concrete on the site, you may be losing 5,000, 7,000, 10,000 rupees. You lose even 1 cubic meter of UHPC on the site, you're losing 1 lakh rupees right away. So yeah.
Just to, sorry, I think, see, because it's very important, maybe audience also may like to understand. See, when you say that this is X cost is there of the UHPC and different material cost requires some cost, and quality control requires some cost. See, is there any something kind of the for guidelines that, okay, 10% is for that, 20% for this, 10% maybe for the cement. How much, see, because this very, I think, right now the UHPC awareness has started, and maybe everybody want to, everybody want to use the UHPC, but they may not knowing that, okay, why the material is costing so much. Okay. And so, see, it is everybody eager. Okay, let also understand that, okay, they want to also produce, or they want to say even buy from some agencies, where this cost is coming from.
So if I had to answer, I'll answer in more than one line. But if I had to answer this in one line, you're not purchasing a material, you're purchasing a technology, basically, because the technology evolves everywhere from a cost of R&D to the material to the business itself, and trying to make and sell something, government taxations, of course, notwithstanding, to the quality assurance and the quality control on the site as well. So there's two levels of quality control and quality assurance. One is in the manufacturer's place, and the other is right there on the site, correct? And there is a percentage that is really wide outside over there. So you could say the cost of raw materials, it by itself, uh, if you're saying 80,000, then out of that, maybe 55,000 odd plus would be just the pure raw materials, leaving out very small to run a business, right? You got to run everything in a plant, in a manufacturing, packing, transportation, marketing, all those kind. I mean, if we talk about business by itself. Yeah.
I think let's move on to the next question. Actually, this is related to code of practice. Like, do India have a code of practice, or no currently available code of practices in the world? Being there in the panel, it's interesting to ask you. Please.
Yeah, I mean, we are a few of us sitting over here who are trying to put the code together. So yes, currently, of course, for the audience in general, yes, India does not have a code right now, and the IRC has a committee B4.5, which is working hard on putting together the code. Code of practice for UHPC, both from a design standpoint and from a quality standpoint and production standpoint, everything. So hopefully in a year's time we should see the light of the day. That is where the thing is. But one thing to realize is the technology itself evolved somewhere in the 1975, 1978. So it's almost a 50-year-old technology, and which has the amount of research that has been done is tremendous already. The usage, if we speak of Denmark, 30 years back, they have already done everything that is currently being done all around the world. So they've already done all of that. And so France has developed their own code, Switzerland has their guidelines, Germany has their guidelines, Japan has their guidelines, China has some little thing of their own. US, after testing it out since 2003, then in 2023 they finally came out with their AASHTO code. After all those couple of decades of work, that is when they finally came out with their code. So as a major country in the world, probably right now we are the last in adopting UHPC, and so our code is going to be probably last in the line to come. But yes, it is going to come in a year, and I think post that the BIS should also pick it up and put together the code.
Yeah. So there is one line of question which is continuous. So what is the standard deviation you have observed in the material, both in compressive and tensile property, and which is that influencing the partial safety factor significantly? It's a combination of.
So interesting thing when it comes to tension, right? There are two types of tests which are available. The easier test being the prism test, which we do for the flexure, and then we do an inverse analysis to find out the direct tensile stress strain curve. But then we don't limit it to three, right? Because of the variability of the fiber direction and all of it. So there are codes that ask for 5 or even 8 samples out there, and because each of these samples will give you a very different curve, and then you come out with some kind of an equivalent statistical fit in between. But in terms of direct tension with a 2% by volume smooth fibers, 0.2 mm by 13, you may be able to see a variation of 8 MPa to 11 MPa at the in terms of the tensile stress, and then it's almost a flat strain hardening curve until strain softening starts, basically. So that's as far as the tension goes. But as far as compression goes, again, uh, if you're talking about just one set of mixes, yeah, you may be in that range of 5 MPa or so, but there was maybe even 6 7 MPa. But here it is that I want to say that the one project where we checked thoroughly over an entire month, on one project, that yielded a standard deviation of 8 MPa, the median being 186 MPa, the highest number being 201 on site, and the lowest probably being 173 or something like that, but a typical standard deviation of about 8 MPa on that.
So can that influence the partial safety factor? Do we have a different number for the design application?
Not necessarily so much. The partial safety factors are nicely given, though, in both the French and the Swiss recommendation. I think one of the things that probably needs a lot more work is on the risk analysis and the probabilistic analysis, because, well, I think, in general, UHPCs, we hope, the UHPCs are all going to be quality UHPCs that are going to come out, right? Because of the care that needs to be taken. That we might be undervaluing the UHPCs a little bit, right? And so there is a waste of resource right around there if we are going to lower our partial safety factor, or have a higher partial safety factor, so as to speak out there. Just for example, you might have a factor of 0.4 on your compressive stress on concrete, 0.4 or 0.45 when you're designing it, right? If you start extending it to the same when it's 150 MPa or 200 MPa, let's say in the future 250 MPa, there is a whole lot that you're going to be missing out on, because the concrete, you see after 0.4 FCK, you can see the nonlinear action happening. But in UHPC, up to 95% plus, you have a linear compressive curve. So, that fit itself is not right. Now, if you take the French code, for example, and if you put down all the numbers, instead of the 0.4 or 0.45, we are going to see about 0.56 times FCK as the number out there.
Okay. Thank you, Dr. Jain. Two more questions from the material side, then I'll move on to the two questions from structures, and we can close it there. Yeah. So can we use M-sand in UHPC mix?
Can we use M-sand? Have to be extremely, extremely careful. I say that because there are two things, the quality control on the M-sand. When the M-sand is coming out, let's say wet, let's forget about the air classified ones, because it has the silt content over, it surrounds the M-sand, and you really don't get good results out of it. Your flow kills itself. We have done several tests over it. But if it's a washed, sand, uh, number one, M sand doesn't typically go through the same drying process. Second thing, as it falls down, there is a segregation of the grading that happens, and you don't know what you're picking up when you're picking up from a heap, when a truck is picking up from a heap. So the variability might be quite high in that sense. Plus the shape factor of your sand itself, what kind of a crusher is it coming from, can really affect the flowability again on it. So I'm not particularly speaking about the strength, but really from the other performance perspectives, like flowability and durability, all of those might really get affected. So although I'm not a great fan of AmSand, but not that I want to put a stamp on it and say that nobody can do a research or anything like that. Things can be looked at definitely in the future. Yeah.
What kind of admixtures you're using? Anything specific to be careful with while we use them?
Well, I mean, admixtures, I think world over now, everybody knows that PC works best, for even for concrete, and PC works best for UHPC as well. So you just need to have a PC. Now, PC also might have different polymers inside of it, but the way it needs to be there is the one that can uh, really disperse your silica fume very nicely, not just the cement. So if you can have a high-end PC that can do that dispersion very well of the silica fume, or your highly reactive pozzolans, as compared to the cement, that will do you greater justice in that sense.
So any specific research has done on the seismic performance of UHPC, and especially in the ductile detailing? Is there any specific corrections has been done when we use UHPC?
So there has been a variety of tests that has been performed at the Florida FIU, at the FIU in Florida, and they have done variety of testings. Now, of course, the question, that we should not think that there cannot be any rebar or UHPC is devoid of rebar. You will need the ductile detailing to some good extent, and you need to provide those. Just that maybe it could reduce slightly because of the heavy duty fiber content and all of it. But yes, testing has been done. One has to realize that because the voids are lesser, right? From a fundamental point of view, the supposed ductility is probably lower in the seismic, but at the same point of time, if you are able to provide enough ductile detailing, and that is what some of the peer testings and column testings that have been done at FIU very clearly shows, all these variations and all these tests that have been done, that yes, to a good account, if you're detailing it appropriately, you can utilize it for your seismic. Plus another thing, UHPC in beam column joints, moment frame beam column joints, have performed excellently compared to concrete in terms of the joint shear. So
Yeah.
that is something that needs to find a mention in some of our codes sooner or later, because when you're doing the modern age buildings, there is a lot of pressure on the joint itself from a design standpoint of view, because the joint shears are very high, and that is where UHPC can substitute the concrete in that joint region very easily.
Correct. Yeah, so there is one another question. Can we use this for deep foundations like piles or probably a diaphragm wall? They would be looking for.
Yeah.
Can we
So
use them?
deep foundations, yes. There are, in fact, examples in Canada and the US where, alternate to steel edge piles have been created using UHPC,
Okay.
and they have been used successfully. So yes, those examples are existent for deep piles.
Yeah. Yeah. So can it be a replacement to shotcreting or micro concrete? That's
Yes, I would say yes, not from a bulk quantity of shotcreting,
Yeah.
you don't want to waste that much amount of UHPC, but or use that much, I would say. But UHPC can be shotcreted in thinner quantities, which should provide the required amount of durability. Uh, Even if it is just about 10 to 15 thick, on certain areas, it could provide tremendous amount of advantage to the durability of the concrete behind it.
Okay. So this is probably the second last question. It's to all of us, basically. We are saying UHPC is in technology. Are we bringing in a prescriptive design code or a performance-based design code?
Yeah, I mean, that's a matter of debate in our meetings always, right? And they see, one of the things is you're using a modern material and you want to be performance based at the same point of time, because you're bringing it out to the public in general. And the code policy members want to take those careful steps. So I think it's going to be some kind of an even mix of the two that the code is going to come out to. I know some people who are not so interested on the research side, but are very much focused on the design. They would like to see quite prescriptive based design, because it's straightforward and they're able to design it. But those who are more inclined toward research, they might feel that they are being shackled up a little bit. But you probably will see a combination of the two in the codes.
Yeah. So the last question: what is the limitation of UHPC, and what's the way forward to UHPC? Like, all the aspect.
Right. So I think I mentioned that the limitation is to think that UHPC can replace all your existing material and can just move ahead. Somebody had a question about fire. I'll tell you that fire is not a limitation, okay, but you got to add some polypropylene fibers, a small amount in addition to the steel fibers, about 0.2% by volume of polypropylene fibers to take care of the fire. So you got to know, your limitations in terms of the application. Like if it's a very high impact solution, that 600 micron down sand will perform lesser compared to a 2.3 down. Okay, because the larger the aggregate, it will perform better in terms of impact resistance. So one has to know slight limitations of where your mixed designs are and what your applications are and how you move forward with them. Choosing the right kind of material designs is very important. Plus, those important when you're looking at marine application, underground sea application. The same UHPC will not go under the sea. You have to change that UHPC a little bit, right? You got to think about shrinkage reductions. You got to think about the flowability of it underwater when it goes 100 meters down or whatever it is. So one cannot say UHPC is just one generic mix and we are going to just use that for all practical applications. There is going to be A to Z and more different kind of UHPCs for different applications.
Thank you. Thank you, Dr. Jain, for your experience and insightful UHPC related talk, philosophy to engineering practice. I would like to thank all the participants. We had around 200 plus participants. So thank all of you. And the questions were quite insightful. I could cover probably some 60 to 70% of questions in the limited time. But thank you all participants for your wonderful time. And with this, we'll conclude the section. Thank you all for having a wonderful.
I just want to add couple of things for.
Please.
In fact, for the participants to know that Dr. Bijily is a Young Scientist Award. She has received a Young Scientist Award and from the ICI, and she is doing a lot of academic research on the UHPC, and that's why we have decided to moderate. It was a very good session, in fact, and she has done the moderation as per expectations and maybe exceeded the expectations. She has taken all the points, and of course, Dr. Satish Jain, who is already very famous, and he is doing lot of R&D. Of course, one part is the manufacturing of the UHPC concrete, but second is the utilization of the science behind that. I think, see, Dr. Satish is doing lot of great work on that to bring that technology in India. So thanks to Dr. Satish Jain that who has accepted to give it a session on this UHPC. And third thing, see, I think you also has asked the question about the code and guidelines. See, as expected and as said by Dr. Satish, the guidelines are being prepared. Now, whether it is a performance base or whether it is a general base, see, I think committee thinks that it has to be first reach to the common mass and people so that they can use the UHPC concrete, because once the guideline is prepared, it is not only the design, there's methodology, construction aspect, material, its behavior, everything has to be considered when this new kind of material is proposed. I expect that some parameters will be performance based, like say tension and all those things also are the percentage of fibers in that. So let us see, but I hope that guidelines will come soon. And Dr. Bijily and Dr. Satish also part of that committee. Thank you.
Thank you so much.
Thank you.
Thank you so much.
Happy New Year to all of us.
Happy New Year to everyone.
Happy New Year. Happy New Year.